So here we have example 1 for using factoring to solve equations. Most of you at this point are going to want to move that 5 over and divide by 10. I don't want to do that. I want to show how I can factor to do this. And so as I look at this, this first example, I see that I could pull 5 out of there. And so I pull 5 out. I'm left with 2x minus 1 equals 0. And then I can inspect these cases. Case 1. Is there a variable here to ever turn a 5 into a 0? In other words, is it like 5x to where you could put a 0 in for the x and then 5x would turn into a 0 and 0 times anything would be 0? No, because 5 is simply a coefficient in this case. You can't change it. We'll ignore it in terms of our cases. The second case, however, you can actually solve this. You can say, okay, 2x minus 1 would be equal to 0 when? And we'll solve it. So we'll move our 1 over, 2x is equal to 1, and then we'll divide by 2. So x would be 1/2. And that gives us a solution here of x equaling 1/2. Probably not the best example to start off with, but I do want you to see that if you pull a constant value out, it doesn't be considered as one of your cases. It's not one of the values you're concerned with. Do a second example here. If I can move my paper. And we're going to do the same thing with this. I'm going to factor first. I see that I could pull 4 out of here, and that would leave me with 3x plus 2. Once again, when you just have a number in the front, it's not really considered a case. You have to have a variable in order to be considered a case. So my only case here is 3x plus 2 equaling 0. I can move the 2 over, so 3x is equal to negative 2. Divide by 3. And as I divide by 3, this gives me an answer of x equaling negative 2/3. So it's just another way of solving these equations. Now as we bump up to the next level, now we're getting some power, because if you get an equation that has a squared component in it, you'll be able to solve it. And so in this case, I look at these two terms, I can pull a 2x out. As I pull a 2x out, it will leave me with an x minus 5. And I have these two cases to consider. Unlike the previous two examples, when I pulled just a number out, I wasn't able to change it. It became a static number. This is dynamic because I can put things in for x. And so the question is, 2x equals 0 when? Now you can either write 2x equals 0 and solve it, or you can reason this out. X is going to have to be 0. To show it analytically, if you divide both sides by 2, I think you would agree that you're going to have x equals 0 over 2, which is 0. And then you have the second case here, where x minus 5 has to be the 0. In order for x minus 5 to be 0, you move the 5 over. X would have to be positive 5. With a finite set of solutions, you would list them out from least to greatest, and we'll use our set notation here. Finite set means we can list all of them in here. We'll say 0, 5. And we'll do another one of these. In this example, we have 3x squared plus 12x equaling 0. So once again, you want to factor it. I can pull a 3x out, and that will leave me with an x plus 4. Every term or every part that has an x is considered a case. So I have two cases here. In case 1, 3x is going to be 0. That means I could divide both sides by 3. X would be 0. And then in my case 2, I could say, well, x plus 4 equals 0. I move that 4 over. X would be negative 4. And once again, once you have these answers, you write a finite set and you list them out. So you say negative 4, 0. And real quick, I want to make sure you understand when I'm saying finite set. If you recall, we solved systems of inequalities, and we solved inequalities. When you solve an inequality and you get something like x is greater than 5, we would do set building notation, where we would say x such that x is greater than 5. And we put all of that in our braces. indicating that there was an infinite number of answers. Anything bigger than 5 would work. So you couldn't list all the answers out, but this was a notation that represented an infinite number of solutions. When we look at this, I have the x on the outside, and I say equal, and then I list all of the components from least to greatest because I can count these. There's 1, 2 answers. And so that's the difference between these. This is a finite, this would be infinite. And just to further show you that, we'll put our 0 here, 5, remember that'd be an open circle, it shades this way. That means all these numbers, all those numbers would work, where up here it's just 1, 2. That's all that works. And so that's what we're going to use in this chapter, the finite solutions.